Chapter 1.13.1.2 Device Plugins. Summary. 1. Kubernetes provides a device plugin framework to share hardware resources with Kubelet. 2. It uses a gRPC service for device registration, helping vendors advertise resources like GPUs, FPGAs, etc. 3. Through plugins, resources are advertised and managed safely, ensuring efficient resource allocation. Device plugins. Kubernetes version 1.26 offers a stable device plugin framework that allows vendors to advertise hardware resources like GPUs and high-performance NICs to the kubelet. Instead of altering Kubernetes code directly, vendors can create device plugins for deployment as daemon sets or manually. This framework caters to computing resources needing vendor-specific setups, like InfiniBand adapters and FPGAs. Device plugin registration. This code snippet defines a gRPC service called registration with a single RPC method called register. The register method takes a register request as input and returns an empty message. This service is likely used for registering device plugins with Kubernetes. This YAML code defines a pod named DemoPod with a container named DemoContainer1 that requires two devices of the hardware vendor. Example, foo type. These devices need to be available on the node where the pod is scheduled, and if there are additional devices beyond the required two, they can be used by other pods. The kubelet offers a gRPC service allowing a device plugin to register by mentioning its Unix socket, the version of the device plugin API, and a resource name. This resource name must match the extended resource naming scheme, for instance, nvidia.com/GPU for an NVIDIA GPU. After successfully registering, the device plugin informs the kubelet of its managed devices. The kubelet advertises these to the API server during its node status update. For example, if a plugin registers two devices as foo, the node's status will show two available foo devices. Devices, managed as extended resources, can be requested by users in a pod specification. The management of these resources slightly differs since they can only be represented as integers and not overcommitted. Moreover, devices are not shareable among containers. Example. If a device plugin registers, hardware vendor. Example, foo. A pod can request this resource to execute a particular workload. The nodes with this plugin will reflect these capacities in their status. Device plugin implementation. The code snippet defines a gRPC service interface for a device plugin in Kubernetes with methods for getting device plugin options, listing and watching devices, allocating devices during container creation, getting preferred device allocation, and pre-starting containers with device-specific operations. Initialization phase **. The device plugin begins its workflow by setting up and initializing vendor-specific devices, ensuring they are ready for use. It starts a gRPC service via a Unix socket located at var, lib, kubelet, device plugins, implementing necessary interfaces. Registration and serving mode **. The plugin registers itself with the kubelet through a Unix socket at /var/lib/kubelet/device-plugins/kubelet.sock. After registration, it serves by continuously monitoring device health and responding to the device's state changes. Handling allocate requests **. During the allocate phase, a device plugin prepares devices, such as GPUs. Successful preparations lead to an allocate response, which provides configurations the kubelet uses to convey to the container runtime. Modifications to containers **. An allocate response contains modifications to a container for device access. These include annotations, device nodes, environment variables, mounts, and fully qualified CDI device names, which require specific features enabled in the kubelet and kube API server. Re-registration on kubelet restarts ***. Device plugins must detect kubelet restarts and re-register themselves. A new kubelet instance deletes Unix sockets, and plugins monitor their removal to re-register as needed. Handling unhealthy devices ***. Plugins report device failures through List and Watch Response API. Decrease in allocatable resources occurs, though capacity count remains unchanged. Failed pods may continue to be assigned but can fail depending on their restart policy. Device plugin deployment. You can deploy a device plugin in 3 ways: as a daemon set, as a package for your node's operating system, or manually. This process requires accessing the directory, var, lib, kubelet, device plugins, which needs privileged access, so the plugin must be in a privileged security context. When deploying as a daemon set, mount, var, lib, kubelet, device plugins as a volume in the plugin's pod spec. This approach benefits from Kubernetes automatically placing the plugin's pod on nodes, restarting it after failure, and facilitating upgrades. API compatibility. Previously, device plugins API version needed to match kubelet's version exactly, but since version 1.12, it's no longer a hard requirement. The API is stable since its beta graduation, although changes may occur. Even though the device manager is stable, the device plugin API isn't. Developers should watch for changes, support multiple API versions, and upgrade plugins to ensure compatibility during node upgrades. Monitoring device plugin resources. The code defines a gRPC service called Pod Resources Lister, which provides information about the node resources consumed by pods and containers on the node. It includes methods to list pod resources, get allocatable resources, and get specific pod resources. This code snippet enables 2 feature gates in Kubernetes: dynamic resource allocation and kubelet pod resources dynamic resources. These feature gates allow for dynamic resource allocation and the ability to manage pod resources dynamically in the kubelet. The code defines several message types used in the list pod resources response gRPC response, including pod resources which contains information about node resources assigned to a pod, container resources which contains resources assigned to a container, container memory which describes memory and huge pages assigned to a container, and dynamic resource which provides information about devices assigned to a container through dynamic resource allocation. Each message type contains specific fields and nested messages to represent various resource allocations and hardware topologies within Kubernetes. The code defines a message structure called allocatable resources response that contains information about all devices recognized by the kubelet. The message includes a list of container devices representing devices available for allocation, a list of CPU IDs, and a list of container memory objects providing memory information. This structure is used to communicate the allocation status of resources to the kubelet. The code defines a message type getPodResourcesRequest that contains information about a specific pod, including its name and namespace. This message can be used to request information about the resources assigned to a particular pod from the kubelet. The pod name and namespace are specified as string fields with numeric identifiers for easy referencing within the message. This code sets the feature gate kubelet pod resources get to true, enabling the kubelet to retrieve information about pod resources. This allows the kubelet to access details about the resources consumed by pods and containers on the node. This feature can be useful for monitoring resource utilization and allocation within a Kubernetes cluster. This code enables 3 feature gates for the Kubernetes cluster: kubelet pod resources get, dynamic resource allocation, and kubelet pod resources dynamic resources. These feature gates allow for dynamic allocation of resources, retrieval of pod resources from the kubelet, and management of dynamic resources within pods. The Kubernetes version 1.28 version allows for advanced resource monitoring via device plugins. These plugins help monitoring agents identify and describe containers by using Prometheus metrics that adhere to Kubernetes instrumentation guidelines. This ensures that containers are properly labeled using pod, namespace, and container Prometheus labels. The kubelet, acting as a service, provides a gRPC endpoint called list to help identify resources and their usage on the node. This informative endpoint returns data on devices used by running pods, including exclusive CPU IDs, device plugin reported device IDs, and NUMA node allocations. In Kubernetes version 1.27 and beyond, the list endpoint can also provide insights on resources allocated via resource claims, influenced by the Dynamic Resource Allocation API. This requires initiating kubelet with specific flags and identifies exclusive CPU allocation for individual containers. The getAllocatable resources endpoint is crucial for identifying allocatable resources on a worker node. It is used when there's a need to decide on available CPUs and provides an initial resource picture, which rarely changes unless external modifications like device health affects it. Monitoring agents that use the kubelet's gRPC services must have privileged access to the directory, var, lib, kubelet, pod resources. If using daemon sets, this directory should be mounted as a volume in the monitoring agent's pod spec to ensure kubelet service restarts with durable connections. The get endpoint introduced in Kubernetes version 1.27 alpha brings similar insights to those offered by the list endpoint but focuses on a specific running pod. This requires inputs like pod name and pod namespace, and dynamic resource allocations are possible with proper kubelet configuration. Device plugin integration with the Topology Manager. The code defines a message structure for representing the hardware topology of resources. It includes a list of NUMA nodes, each identified by an integer ID. This structure allows for specifying the topology information for devices assigned to containers based on the NUMA nodes. The code snippet creates a device object with ID 25,102,017 and sets its health status as healthy. It also assigns a topology information to the device, specifying that it is connected to NUMA node ID 0. Kubernetes version 1.27 introduces the Stable Topology Manager, which coordinates resources in alignment with system topology through the kubelet. The Device Plugin API has been expanded to include topology info, enabling devices to register with detailed topology data, such as NUMA node alignment and device health status. Topology Manager uses this topology data to assign resources efficiently, even for devices spanning multiple NUMA nodes. A topology without NUMA preference is indicated by setting topology info to nil. Device plugin examples. Kubernetes hosts a variety of third-party projects that enhance its functionality. These projects are added through a specified content guide and are listed in alphabetical order. The responsibility for these projects falls outside Kubernetes author's jurisdiction. One such project is Acree, simplifying the exposure of various peripheral devices like IP cameras and USB devices. Others include device plugins catering to AMD GPUs, generic Linux devices, Intel hardware, and NVIDIA GPUs. Additional device plugins support specialized hardware like KubeVirt for virtualization, RDMA communication, SocketCAN for networking, and others like SolarFlare and SRIOV network for device-specific tasks.